So here's a strange thought to start with. What if being wrong is actually the best thing that can happen to you? I know, it doesn't sound very flattering. Nobody wakes up in the morning hoping they'll embarrass themselves with a mistake. But in mathematics, in science, in basically everything humans do, being wrong has been one of the biggest engines of progress. In fact, you could almost say that mistakes are the unpaid interns of history. They work really hard, they don't get any credit, and in the end, they change the world. Think about it. Every great discovery, every brilliant equation, every sparkling idea is basically surrounded by a graveyard of failed attempts. Humans don't just stumble on truth in one go. We bump into it, spill our coffee on it, kick it under the table, and then 100 years later someone else trips over the same thing and says, wait a second, this might actually be useful. The thing about math is that people usually think of it as perfect. Like 2 plus 2 will always equal 4. No discussion. Math is supposed to be this cold, flawless temple where everything fits together in harmony. And that's true once we figure things out. But the path that got us there is messy, full of bad guesses, wrong assumptions, wrong numbers, and sometimes just hilarious accidents. The history of math is less about genius minds writing neat equations on a board, and more about confused people wrestling with problems they barely understood, making errors that sometimes turned out to be more interesting than the correct answer. Let me give you a simple example. If you've ever tried to measure something with a ruler, you know you can make mistakes. You might line it up wrong, misread the scale, or forget whether you were using inches or centimeters. That's just daily life. But imagine doing that same thing on the scale of building pyramids or sending rockets to space. Suddenly, that tiny mistake can turn into history-making chaos. And that's exactly what we'll be exploring in this video. The times when math went horribly wrong and humanity ended up better for it. One of the funniest parts about this is that mistakes are often only visible in hindsight. At the time, they usually look like good ideas. For example, in ancient times, people believed that the Earth was the center of the universe. That wasn't because they were dumb. It was actually a very reasonable mistake. You look up at the sky, the stars seem to spin around you. The sun rises and sets. Of course it feels like we're in the middle. They even built very sophisticated math around this wrong assumption, predicting the movements of planets with weird circles inside circles. For centuries, this wrong math was considered cutting-edge science. Then, one day, Copernicus and Galileo show up and go, oh, by the way, we're not actually the center of everything, and the whole cosmic stage flips upside down. That kind of story repeats everywhere. Wrong turn, wrong assumption, wrong number. And yet, from those errors, we somehow get closer to the truth. There's almost something comforting about that. You don't need to be perfect to move humanity forward. You just need to be wrong in an interesting way. Let's also admit something. Mistakes are funny. A perfectly correct equation is impressive, but it's not exactly entertaining. Nobody has ever said, wow, look at that flawless quadratic formula. I laughed so hard. But mistakes, those can be hilarious. Like the time NASA lost a $125 million spacecraft because one team used metric units and the other used imperial. That's not just a mistake. That's a cosmic level oopsie, and we'll get to that later in the story. But before we zoom in on those specific disasters, I want to stay with this idea of mistakes being beautiful. There's a strange poetry to it. Humans are obsessed with certainty, but we actually thrive on uncertainty. If we already knew everything, there'd be no progress. The reason math has grown from people carving marks on bones to people exploring the edges of black holes is because we kept messing up along the way. And every time we messed up, we learned something we didn't know before. And here's another funny twist. Some of the biggest mistakes in math weren't even mistakes at all. They were just things that looked wrong to everyone else at the time. Take imaginary numbers, for example. The square root of -1. For centuries, mathematicians thought this was nonsense. You can't take the square root of a negative number, they said. That's impossible, meaningless, garbage. But then people started using it anyway, as a kind of bookkeeping trick. And eventually, those so-called nonsense numbers turned out to be essential for modern engineering, electricity, quantum physics, even your phone. Without that wrong math, you wouldn't even be listening to this video right now. So maybe the moral here is that being wrong isn't always about being foolish. Sometimes being wrong is just being early. Now, you might be thinking, okay, this is all very philosophical, but where are the juicy stories? Don't worry, they're coming, because history is packed with juicy, hilarious, sometimes tragic mathematical mistakes. Whole civilizations have stumbled because of math errors. Wars have been fought, fortunes lost, bridges collapsed, and calendars reset. All because somewhere, someone misplaced a number. But before we dive into those specifics, let me confess something. I love mistakes. I really do. There's something deeply human about them. They make history feel less like a parade of geniuses and more like a bunch of people fumbling around in the dark, occasionally bumping into brilliance. When you look at the story of math through the lens of mistakes, it stops being intimidating. It starts being relatable, because let's be honest, most of us aren't Gauss or Euler or Newton. Most of us are the kind of people who forget to carry the one, who write down the wrong date, who double-check a restaurant bill and still get it wrong. And yet, that's the exact same process that gave us calculus, relativity, and the internet. So, in this series of stories, I'm going to celebrate the wrong turns. We'll meet the ancient mathematicians who trusted geometry a little too much, the people who hated zero, the Romans who made math unnecessarily complicated with their clunky numerals, the philosophers who wrestled with infinity until their brains melted, and the engineers who underestimated the power of wind on a bridge. And of course we'll laugh at the modern-day mistakes too, from failed computer programs to billion-dollar math slip-ups. The point is not to mock these mistakes, but to enjoy them, to see how every stumble actually carried us forward. It's like climbing a mountain, but constantly tripping over rocks. Each fall hurts, but every time you stand up, you're a little higher up the trail. So let's start this journey. We're going to walk through history, not with the eyes of a perfectionist, but with the curiosity of someone who knows that the most interesting stuff happens when things go wrong. Because in the end, math is not about cold perfection. It's about human beings with all our flaws and quirks trying to make sense of the universe. And honestly, the universe seems to enjoy watching us struggle a little before giving up its secrets. And maybe, just maybe, by the time we're done, you'll start to love mistakes as much as I do. Or at least, you'll laugh at them. Counting. It seems so simple. Right, 1, 2, 3, 4. Kids can do it before they can tie their shoes. Dogs can count treats, at least up to 2 or 3. Even crows know when one peanut has mysteriously vanished. Counting feels like the most basic, obvious thing in the world. But here's the twist. For most of human history, counting was a complete disaster, and when people tried to build calendars, trade goods, or track harvests, their mistakes were legendary. Let's rewind far, far back. Imagine you're a hunter-gatherer thousands of years ago. You don't have math. You don't even have a written language. But you've got problems. You need to know how many animals are in the herd. You need to remember how many days until the berries ripen. You need to keep track of how many sharp rocks you've turned into spearheads. The earliest humans solved this with sticks. Literally, they carved notches into bones and sticks to represent numbers. Archaeologists have found bones from 20,000 years ago, with little scratches that clearly meant something. The problem was, nobody really standardized this. One notch might mean one deer to you, but maybe it means 1 week to someone else. And if you break the stick, congratulations, your accounting system just reset itself. Fast forward a little to the first farming societies. Now people really needed math. If you're planting crops, you have to know when the seasons start, how long until the flood comes, and how much grain you've stored. Here's where mistakes started getting funny. The Egyptians built calendars based on the flooding of the Nile, but they weren't exactly precise. Their early year was 360 days long. Then they realized that wasn't working, so they added 5 bonus days at the end of the year. Imagine celebrating your birthday, and then someone tells you, oh wait, we've got 5 extra days this year for no reason. Happy bonus week. And still, even with that adjustment, their calendar drifted. Over centuries, the months slowly marched away from the seasons. You'd have festivals for planting crops in the middle of the dry season. Oops, the Babylonians had their own mess. They decided to build their math system around the number 60. Why 60? Because it divides nicely into many factors. Sounds clever, right? Except it led to some pretty confusing counting. If you've ever wondered why there are 60 minutes in an hour or 360 degrees in a circle, you can thank those Babylonian number nerds. But the problem was, they didn't even have a clear symbol for zero. Imagine trying to keep track of huge numbers without a proper placeholder. You write down 2, then leave a little space, then 5. Was that 25, or 205, or 2005? Depends on how much coffee the scribe had that morning. And then there's trade. Ancient merchants constantly messed up counting their goods. We have tablets from Mesopotamia, where scribes tried to record how many jars of beer were owed to the temple. But because their system was clunky, the numbers are sometimes nonsense. It's like the world's oldest drunk math homework. One scholar even suggested that some tablets might be intentionally wrong, creative accounting that would make even modern tax cheats proud. But here's the funniest part. Counting mistakes weren't just embarrassing, they shaped entire civilizations. Take calendars again. The Romans were notorious for messing with theirs. At one point, their year had drifted so badly that winter festivals were happening in the fall. Julius Caesar eventually had to step in and say, all right, enough is enough. We're resetting the whole thing. He introduced the Julian calendar in 46 BCE, but even that was off by about 11 minutes per year. Doesn't sound like much, right? But after centuries, those minutes piled up and suddenly Easter was drifting into summer. This would later lead to the Gregorian calendar reform, where they literally deleted 10 days from the year 1582. Imagine going to bed on October 4th and waking up on October 15th. People thought the church had stolen their lives. Nope, just bad counting. And construction. Oh boy. Ancient builders relied on counting and measuring with ropes, rods, and sight lines, and sometimes they got it wrong. Archaeologists have found temples and pyramids where the sides don't quite line up, or where the steps gradually shrink in size like someone lost count halfway through. Of course, we admire these monuments today, but you can't help but imagine a stressed-out foreman yelling at some poor worker, I told you it was 42 blocks, not 41. Now the gods are going to be crooked forever. One of my favorite ancient counting blunders comes from the Mayans. They were brilliant mathematicians in many ways, inventing the concept of zero long before Europe caught on. But their calendar system had cycles that occasionally overlapped in weird ways. According to some interpretations, they basically predicted the end of the world in 2012. That was a counting glitch that went viral thousands of years later. People panicked, movies were made, survival bunkers sold out, all because of ancient math that wasn't even wrong, just misinterpreted. Humanity loves a good counting mistake, apparently, but don't get the idea that ancient people were dumb. Their mistakes were completely natural for the tools they had. Imagine trying to calculate the length of a year without telescopes, precise clocks, or calculators. You're just eyeballing the sun, scratching marks on stones, and hoping you don't lose track. Honestly, the real miracle is not that they got things wrong, but that they got so much right. Still, the wrong turns gave history its flavor. They forced people to invent better calendars, better systems, and eventually better math. And in a way, counting mistakes are still with us. Have you ever noticed how we can't even agree on the number of continents? Some say 7, others say 6. In some schools they teach 5, That's basically a modern version of the same problem. Or think about counting calories on a diet. Are you absolutely sure that slice of pizza was 250 calories and not 400? Congratulations, you're continuing the proud human tradition of miscounting things. So what do we learn from all this? The first step in mathematics, counting, wasn't straightforward at all. It was messy, confusing, and often hilarious. But from that mess, entire systems of numbers, calendars, and civilizations emerged. Every mistake pushed humanity to refine the way we track our world. And even if people didn't realize it at the time, those little counting oops moments were laying the foundation for everything that came later. In the next chapter, we'll see what happened when geometry, the so-called queen of mathematics, decided to lie to humanity for a couple of thousand years. Spoiler alert, the Greeks were very confident, very persuasive, and also very wrong. Geometry. The very word sounds trustworthy. It comes from the Greek words for earth and measurement. That's serious business. The Greeks believed geometry was the purest, most perfect kind of knowledge humans could ever reach. They treated it like a holy language, the closest thing to divine truth. If arithmetic was for shopkeepers, geometry was for philosophers. It was supposed to be flawless. But here's the punchline. Geometry lied to them for over 2,000 years. Let's rewind to ancient Greece. Imagine Athens with its marble temples, sweaty philosophers in togas, and people arguing about triangles under olive trees. This was the birthplace of Euclid's Elements, a book so famous it became the geometry Bible. For centuries, students all around the world learned straight from Euclid. His book was considered perfect, almost sacred. The problem was, it wasn't. Hidden inside that beautiful system were assumptions that weren't actually true. But the Greeks didn't notice. Or maybe they did, and just shrugged. The biggest culprit was something called the parallel postulate. Now, don't panic. I'm not going to dump a chalkboard of equations on you. Here's the simple version. The parallel postulate said that if you draw one line, and then a point not on that line, there's exactly one line through that point that never touches the first one. In other words, parallel lines exist and behave themselves. Sounds obvious, right? Look out your window, your street, your bookshelves. Parallel lines are everywhere. But here's the twist. Mathematicians spent literally centuries trying to prove that postulate from the other rules of geometry. They thought it was redundant, like a spare tire you didn't need. They failed, over and over, and they got frustrated. Some even called it the ugly duckling of Euclid's system. The thing just wouldn't behave. Still, instead of questioning it, they clung to it like a bad relationship. For 2,000 years, geometry was built on an assumption nobody could prove. Meanwhile, geometry was out there lying to people in very practical ways. Surveyors used it to measure land, architects used it to design temples, and navigators used it to sail the seas. And for small scales it worked beautifully. But if you zoomed out to the size of planets or zoomed into curved surfaces, suddenly the math started to get weird. Imagine drawing a triangle on the surface of a sphere, like the Earth. You pick the North Pole, and then 2 points on the equator. Connect the dots. Surprise. Your triangle has 3 right angles. That's 270 degrees, not 180. Geometry was basically catfishing humanity, pretending to be universal truth, but actually just a local approximation. And the Greeks weren't the only ones fooled. Medieval scholars inherited Euclid and treated him like gospel. Geometry became the foundation of astronomy, art, architecture, even theology. Cathedrals were built according to geometric principles. Artists used perspective grids. Theologians used circles and spheres to imagine heaven, all based on a geometry that wasn't telling the whole truth. It took until the 19th century for people to finally say, wait a second, what if the parallel postulate isn't true? What if space itself is different? Enter Gauss, Bolyai, and Lobachevsky. These guys dared to imagine geometries where parallel lines don't behave. In one version, there are infinite lines through a point that never meet the first one. In another, there are none. Suddenly, geometry exploded into new worlds. Non-Euclidean geometry was born, and it turned out to describe reality better than Euclid ever could. Einstein later used it to build general relativity, the theory that explains gravity as the curvature of space-time. So, the lie of geometry eventually gave us the truth about the universe. But think about the comedy of it. Humanity spent 2 millennia doing math homework on the wrong assumptions. Entire civilizations built their intellectual systems on a foundation that was shaky from the start. It's like finding out your GPS has been calibrated for flat Earth. Sure, it'll get you to the grocery store, but good luck navigating to the moon. Here's a fun little side note. The obsession with the parallel postulate actually drove some mathematicians insane. They'd spend decades trying to prove it, scribbling diagrams until their eyes hurt, and then dying unsatisfied. It was like a math version of chasing Bigfoot. You're convinced the truth is out there, but all you find are blurry footprints. And yet, this giant collective mistake wasn't a waste. It forced people to think harder, to question assumptions, to imagine alternatives. The very stubbornness of geometry pushed humanity toward breakthroughs it might never have reached otherwise. If Euclid had been perfect, maybe we'd never have discovered relativity. Maybe we'd still be drawing triangles under olive trees, convinced the universe is a flat board game. There's also something poetic about geometry's betrayal. The Greeks thought math was eternal and absolute, but the universe whispered back, not quite. Space is flexible, curved, mysterious. Parallel lines don't always play nice. The truth turned out to be stranger and more beautiful than the lie. So, the moral here, don't trust a system just because it looks neat. Sometimes the neatest systems are hiding the biggest mistakes. And when geometry lied, it didn't just trick a few students on their homework. It shaped how humanity saw reality itself. Next time, we're going to talk about 0, the number that scared people, confused them, and got treated like mathematical black magic. If geometry lied, 0 was the ghost that haunted mathematicians for centuries. Let's talk about nothing. Not in a poetic, late-night philosophy way. I mean literally the number 0. On the surface, 0 looks harmless. Cute little oval. Doesn't count for much. But don't let appearances fool you. 0 has probably caused more arguments, more confusion, and more panic attacks in math history than any other symbol. It's the mathematical equivalent of a horror movie ghost. Everyone knew it was there, but nobody wanted to admit it existed. Why would anyone be scared of nothing? Well, let's put ourselves in the sandals of an ancient mathematician. You're living in a world where numbers are practical. Numbers count sheep, jars of wine, days until harvest. But what about nothing? How do you count nothing? Do you really need a number for no sheep? You'd just point at the empty field and say, there are no sheep. Simple. The idea of making that emptiness into a number felt weird, even dangerous. The Babylonians, as we saw earlier, kind of flirted with the idea. They sometimes left a space in their cuneiform to mark nothing here. But it wasn't a true 0, more like a placeholder, like leaving a blank in your grocery list. Buy 3 fish, blank bread, 5 onions. Confusing. The real invention of 0 as a number seems to have happened in India. Around the 5th century, Indian mathematicians started using a dot to represent nothing, and eventually that dot became the round 0 we know today. They didn't just see 0 as an empty hole. They treated it as a number you could actually work with. You could add it, subtract it, even use it in equations. Revolutionary stuff. But when this dangerous little circle traveled to other cultures, people freaked out. In medieval Europe, the church and many scholars distrusted it. Some even thought 0 was connected to the devil. After all, God created everything. Right. How could there be a number for nothing? That smelled suspiciously like heresy. Merchants, on the other hand, loved zero because it made bookkeeping way easier. But they had to use it carefully because people accused them of using Arabic numerals to cheat. Yes, you heard that right. The number zero was once considered a tool of fraud. There's also the terrifying math problem of dividing by zero. Even today, your calculator has a meltdown if you try it. It flashes error and sulks. Why? Because division is basically asking, how many times does this number fit into that number? If you ask, how many times does zero fit into 5, the universe just shrugs and says, what are you even asking me? Ancient mathematicians realized quickly that dividing by zero doesn't make sense. Some declared it impossible, others tried to sneak around it with weird rules, and every attempt led to confusion. In some cultures, zero was banned from serious math altogether because of this nightmare. Here's a funny story. In the 13th century, the Italian city of Florence actually outlawed the use of zero in banking records. They claimed it was too easy to forge numbers. Turn a 0 into a 6 or an 8 with a couple of strokes, and boom, you've stolen money. Instead, they forced merchants to write nothing with words. Imagine modern accountants writing 10,000 nothing nothing instead of 10,000. Bureaucracy at its finest. But zero refused to go away. It spread because it was just too useful. It made positional number systems possible. Without zero, you can't tell the difference between 52 and 502. Without zero, you can't do advanced arithmetic. Without zero, computers literally wouldn't exist. Every byte of information your phone uses is based on 0 and 1. So, the number that people once banned as devilish nonsense is now the backbone of the digital age. And yet, even today, zero plays tricks on us. There's the famous paradox of dividing by zero we mentioned, but also think about the concept of nothing in physics. Is a vacuum really nothing? Quantum mechanics suggests even empty space is buzzing with energy. Suddenly, zero doesn't feel so empty anymore. It feels alive, mysterious, powerful. Philosophers love to get tangled in this too. Medieval thinkers debated whether nothing could exist. Some said nothing is the absence of being. Others argued nothing is something in itself. It's the kind of argument that sounds deep at first, but eventually makes you want to bang your head on the desk. And mathematicians weren't immune either. They constantly fought about how to handle this little symbol. Was it really a number, or just a placeholder? Did it have meaning, or was it just a trick? Of course, once calculus showed up in the 17th century, zero got even more dramatic. Calculus is built on the idea of approaching zero, getting infinitely close to nothing but never quite reaching it. Suddenly, zero wasn't just a number, it was a cliff edge, a place where infinity and nothingness shook hands. The very tools that let us calculate the orbit of planets and the flow of electricity depend on this dangerous flirtation with zero. Here's my favorite irony. The number zero, once considered evil, now underpins our economy, our technology, and our science. If you deleted zero from history, we wouldn't have computers, rockets, or even modern accounting. We'd still be scratching notches on sticks. Zero was the most dangerous nothing, but it turned out to be the most powerful nothing too. And maybe that's the lesson. Sometimes the things that look like nothing are actually everything. The mistakes people made with zero fearing it, banning it, misunderstanding it, forced humanity to wrestle with one of the most profound concepts in math. Nothingness isn't empty. It's the key to unlocking whole new worlds of thought. So next time you see a zero, don't underestimate it. That little circle carries centuries of confusion, controversy, and accidental brilliance. It's not just nothing. It's the symbol that proves mistakes can become miracles. In the next chapter, we're going to meet the Romans and their bizarre number system. Spoiler alert, it was clunky, confusing, and absolutely terrible for doing real math. Let's just say if you've ever tried to do long division with Roman numerals, you'll understand why Europe basically stopped advancing in mathematics for centuries. Let's be honest. Roman numerals look cool. They make movie sequels feel important. Rocky 2 sounds cheap, but Rocky 2 with Roman numerals, Rocky 2, feels like an epic saga. Clocks with Roman numerals look classy. Super Bowls use them to feel more like gladiator battles. But behind that shiny, majestic facade hides one of the worst counting systems ever inflicted on humanity. Roman numerals were a mathematical disaster. Why? Because they were never designed for actual math. They were designed for carving onto monuments. They look great in stone, but try adding, subtracting, or, heaven forbid, multiplying with them, and you'll quickly want to sack Rome yourself. Here's how the system worked. Instead of having place value, like our modern numbers, Romans used letters: I equals 1, V equals 5, X equals 10, L equals 50, C equals 100, D equals 500, and M equals 1000. Sounds simple enough, but the rules are clunky. Sometimes you add letters together, sometimes you subtract. IV means 4, IX means 9. But wait, XL means 40. And don't even get me started on 90. It's XC. Already your brain hurts. Now imagine trying to do long multiplication. Let's take something modest, like 27 times 43. In Roman numerals, that's XX57 times XL. How do you even start? Do you write out 27 little tally marks and repeat them 43 times? That's basically what Roman merchants did. They used counting boards, moving pebbles around like an abacus. The numerals were just a record, not a tool. The Romans could build aqueducts and roads. Sure, but their math system made actual calculation painfully slow. This wasn't just inconvenient, it stalled progress. While other cultures were inventing algebra and advanced astronomy, the Romans were stuck doing arithmetic with glorified alphabet soup. No wonder mathematics in Europe stagnated for centuries. When your number system can't even handle 0, you're in trouble. Yes, that's right. Roman numerals had no 0. None. If you wanted to write nothing, you just left a blank, which, as you can imagine, is not ideal for bookkeeping. Imagine balancing your budget with nothing but Roman numerals. Your accountant would quit by lunchtime. Let me give you a sense of the madness. The year 1987 in Roman numerals is MCMLXXV7. That's 9 characters. Meanwhile, in Arabic numerals, it's just 1987. Clean, simple, efficient. If you want to write 1 million in Roman numerals, good luck. They had to put a bar over a letter to mean 1,000 times this. The whole thing turned into a typographical circus. And yet, the Romans stuck with it. They used this clunky system for centuries, long after better systems existed elsewhere. Part of it was cultural pride. Roman numerals were tied to power, tradition, empire. If you abandoned them, it felt like betraying Rome itself. But clinging to them also meant clinging to inefficiency. Imagine trying to calculate the trajectory of a catapult using Roman numerals. By the time you've finished writing out the numbers, the enemy has already invaded. There's an irony here. Rome was famous for engineering: roads, bridges, aqueducts, massive amphitheatres, and yes, those required math. But much of the actual calculation was done using tools like abacuses, not Roman numerals themselves. The numerals were more like a decorative afterthought, so while Roman monuments look timeless with those carved letters, the system behind them was already creaking under its own weight. And here's where it gets funny. When Arabic numerals, the ones we use today, started sneaking into Europe in the Middle Ages, people resisted. They said the new system was suspicious, foreign, even dangerous. Merchants loved it because suddenly math was faster. But officials accused them of using it to cheat. Cities like Florence even banned Arabic numerals for a while. Instead of embracing efficiency, they clung to their beloved Roman chaos. Humanity basically said, "No thanks, we prefer suffering." The eventual victory of Arabic numerals with 0 and place value was like switching from chisels to power tools. Suddenly math could explode into new directions. Algebra, calculus, modern science. But think about how long Europe dragged its feet. Roman numerals had been holding them back for over a millennium. That's a long time to be doing math homework with a blunt stick. Of course, today, Roman numerals survive as decoration. They're like the antique furniture of numbers. Nice to look at, terrible to actually use. You see them on old buildings, watch dials, Super Bowls, monarch names. Queen Elizabeth II looks grand with her Roman numeral. Imagine if she were just Elizabeth II, doesn't have the same gravitas. But here's the deeper point. Roman numerals remind us that not all number systems are created equal. Some are elegant tools for calculation. Others are clunky legacies that just refuse to die. And the Romans accidentally trapped themselves in the latter. Their mistake wasn't inventing Roman numerals. It was refusing to let them go. For centuries, they were stuck with a math system that looked powerful but wasn't. It's the classic case of style over substance. So the next time you struggle with math, be thankful you don't have to do it in Roman numerals. Imagine trying to calculate your taxes as MMMDCC LSXXIGAS plus DLX TOV. That's 3,889 plus 562 if you're wondering. And I had to double check that. Twice. The Roman numeral disaster shows us that sometimes tradition itself can be the biggest mistake. It wasn't a single miscalculation that doomed Roman math. It was the refusal to evolve, and that stubbornness shaped history, keeping Europe's mathematics in the slow lane until a new system finally broke through. In the next chapter, we'll shift back to something that looks simple but drove mathematicians insane for thousands of years. The number pi. People tried to tame it, round it, even solve it once and for all. And spoiler alert, they failed spectacularly. Pi, the celebrity of numbers, the Beyoncé of mathematics. Everyone knows it, everyone loves it, and yet almost nobody truly understands it. On the surface, pi looks innocent. It's just the ratio of a circle's circumference to its diameter. How complicated could that be? Take a circle, measure around it, measure across it, divide one by the other, and boom, you've got pi. Easy, except not really. For thousands of years, humanity tried to tame this slippery number, and along the way they made some spectacular mistakes. Let's start with the basics. Pi is about 3.14159 and so on. Forever. That forever part is what drove people mad. Ancient civilizations desperately wanted pi to be a neat fraction, something simple, like 3 or 22 over 7. Something you could scribble on a clay tablet without losing your sanity. After all, circles are everywhere. Wheels, temples, astronomy, pies. Having a messy number attached to them felt wrong. The Babylonians were some of the first to take a crack at it, around 2000 BCE. They decided pi was about 3.125, close enough for government work. The Egyptians said, no, you fools, it's 3.1605. Still wrong, but hey, at least they were trying. Then came the Greeks. The Greeks. They weren't content with guesses. They wanted perfection. Enter Archimedes, one of the greatest math minds of all time. He came up with a clever method of trapping pi between polygons. Draw a circle, then inscribe a polygon inside it, and circumscribe one outside it. The more sides you add, the closer you get to the true value of pi, with 96 sides. Archimedes got pi down to between 3.1408 and 3.1429. Pretty impressive for a guy without a calculator. But even Archimedes couldn't give the world a neat exact value, and that frustrated mathematicians for centuries. People really wanted pi to be clean. In the Bible, there's even a verse in the Book of Kings that seems to imply pi is exactly 3. The temple basin is described as being 30 cubits around and 10 cubits across. Religious scholars debated this for ages. Was God rounding? Was it a mistranslation? Or did ancient carpenters just stink at measuring? By the Middle Ages, pi had become the math equivalent of Bigfoot. People obsessed over it. They hunted it, chased it, argued about it. They proposed fractions like 355 over 113, which is freakishly accurate to 6 decimal places. But no matter how hard they tried, pi refused to settle down. It was irrational. That's the official math word. Irrational, meaning it can't be written as a ratio of whole numbers, and worse, it's also transcendental, meaning it's not the solution to any algebraic equation. It just is, like a cosmic prank baked into the universe. Of course, along the way, humanity made mistakes. Some were innocent, like using rough approximations in architecture. Others were downright stubborn. In the 19th century, a legislator in the United States actually tried to pass a law declaring pi to be 3.2. Yes, you heard that right. A legal value for pi. The idea was to make math easier for schools and engineers. The bill actually passed one chamber of the Indiana state legislature before someone with actual math skills stopped it. Imagine if they hadn't. We'd all be driving cars with wheels that wobble like shopping carts. And then there were the people who thought they could solve pi, like once and for all. For centuries, ambitious mathematicians announced they had cracked the mystery, only to embarrass themselves. In the 1890s, a doctor named Edwin Goodwin claimed he had squared the circle, solved an impossible problem, and in the process discovered the true value of pi. Spoiler, he hadn't. His proposal was the one that nearly became Indiana law. To this day, squaring the circle is used as a phrase for chasing the impossible. But even the mistakes surrounding pi weren't wasted. Every failed attempt pushed math further. The obsession with pi helped to develop calculus, trigonometry, and infinite series. It inspired computer scientists centuries later to write programs that calculate pi to trillions of digits. And while nobody needs that many digits to build a bridge, the process pushes the boundaries of computing power. There's also a kind of human comedy in the obsession. People celebrate Pi Day on March 14th. Eat pies, recite digits like poems. Guinness World Records keeps track of who can memorize the most digits of pi. The current record is over 70,000, which, let's be honest, is impressive, but also a little bit terrifying. Pi has gone from being a frustrating mistake to a cultural icon. But maybe the most beautiful thing about pi is that it reminds us math isn't always neat. We love whole numbers, clean fractions, round results. Pi laughs at that. Pi says, "Sorry, I go on forever, and you'll never pin me down." It's both humbling and inspiring. The mistakes people made with pi, rounding it, legislating it, trying to trap it, show how deeply we crave order and how often the universe refuses to give it to us. So when pi went wrong, it wasn't really pi's fault. Pi has always been what it is. The mistakes were human, our desperate attempts to make reality simpler than it actually is, and yet those mistakes led us to deeper truths. From Archimedes' polygons to modern supercomputers, the pursuit of pi has fueled mathematical creativity like almost nothing else. The moral: sometimes mistakes don't go away because they aren't really mistakes at all. They're just reminders that the universe is more complicated than our rules. And honestly, isn't that what makes it fun? In the next chapter, we're going to leave circles behind and dive into calendars, because as it turns out, humans are just as bad at measuring time as they are at measuring circles. Get ready for years that drift out of sync, bonus days and centuries of scheduling chaos. Time. We all live by it. Wake up at 7, lunch at noon, work until 5. Easy. Until you ask the terrifying question, how do you actually measure time on the scale of years and seasons? Suddenly, it gets messy. Calendars are supposed to bring order to life. Planting, harvesting, religious festivals, taxes. Without them, civilization collapses. But the history of calendars is basically one long comedy of errors. Humanity has been spectacularly bad at measuring time. Let's start with the Egyptians. They were some of the first to notice that the Nile's flooding happened roughly once a year, and they wanted a calendar to match it. So they gave the year 360 days. Nice round number, very tidy, except the Earth stubbornly refused to orbit the Sun in 360 days. The real number is about 365.25. That left the Egyptians drifting further off every year. Their solution? Just tack on 5 bonus days at the end of the year. Imagine celebrating your birthday, then being told, oh, by the way, after December we've got a little 5-day festival. Nothing special, just extra time we forgot to include. Chaos, but at least it gave them more parties. The Babylonians, never wanting to be left out, came up with a lunar calendar, months tied to the cycles of the moon. That sounds poetic, but it's also a nightmare. 12 lunar months equal about 354 days, which is 11 days short of a solar year. If you don't fix that, your months slowly drift through the seasons. Festivals meant for spring end up happening in winter. Imagine celebrating Easter in August. To patch the problem, the Babylonians sometimes threw in an extra month. Randomly. Whenever things look too out of sync, talk about winging it. The Romans, of course, made the situation even worse. Their early calendar was a mess of 10 months. Starting in March, that's why September, October, November and December literally mean 7th, 8th, 9th and 10th. Except they're the 9th, 10th, 11th and 12th months now. Already confusing. Then they added January and February but still couldn't get the math right. Some years had 355 days, others had 377. Politicians even manipulated the calendar to extend their terms in office. Time itself was being rigged, like an election. Finally, Julius Caesar stepped in 46 BCE. He introduced the Julian calendar, with 365 days and a leap day every 4 years. Much better. Except it was still off by about 11 minutes a year. Tiny error, right? But over centuries those 11 minutes added up. By the 1500s, the calendar was out of sync by about 10 days. Easter was sliding towards summer. Priests were panicking. Farmers were confused. People started blaming the church for stealing time. So, Pope Gregory XIII launched a fix in 1582, the Gregorian calendar. He ordered that October 4th would be immediately followed by October 15th. 10 days erased. Just like that. People lost their birthdays. Rent payments skipped. Whole chunks of life disappeared overnight. In some places, riots broke out. Imagine going to bed one day and waking up in the future. Hey, what happened to my week? Sorry, the Pope deleted it. That's the kind of chaos only humans could invent. And here's the kicker. Not everyone adopted the Gregorian calendar at the same time. Catholic countries switched quickly. Protestant ones resisted. England didn't adopt it until 1752, by which time they were 11 days behind. Russia didn't adopt it until after the Bolshevik Revolution in 1918. That's why the October Revolution actually happened in November by our modern calendar. Humanity couldn't even agree what day it was. Wars were fought, treaties signed, holidays celebrated, all on mismatched calendars. But the comedy doesn't stop there. Even with the Gregorian fix, we're still fudging things. Leap years are a patch job to keep the calendar in sync with the solar year. Every 4 years we add an extra day. But that's still not perfect, so we skip leap years on most centuries. Except if the year is divisible by 400. That's why the year 2000 had a leap day. But 1900 didn't. It's like a cosmic game of gotcha. And still, the system drifts by about 26 seconds per year. We've just learned to live with the chaos. And then there's daylight saving time. Humanity's boldest attempt to prove we have no idea what we're doing with clocks. First introduced in World War I to save energy, it's now mostly just a ritual of confusing everyone twice a year. We literally change our clocks back and forth like a child playing with Legos. Farmers hate it. Parents hate it. Scientists say it doesn't even save energy anymore. But we keep doing it because tradition, the calendar chaos continues. What's fascinating here is how these mistakes shaped culture. The Egyptians invented bonus festival days. The Romans left us with confusing month names. The Gregorian reform sparked centuries of conspiracy theories. Even today, you'll find people who believe the missing 10 days are proof that history itself has been faked. All because humans couldn't quite nail down the length of a year. And let's not forget, some cultures solve time differently. The Mayans built their own complex calendar, with overlapping cycles that occasionally reset in dramatic ways. That led to the infamous 2012 doomsday prediction. Spoiler, nothing happened. Just another case of humanity misreading math. Again. So what's the lesson? Measuring time is hard. Really hard. Our planet doesn't orbit neatly. The moon doesn't sync up perfectly. And humans are terrible at rounding. The calendar chaos shows that even the simplest seeming math, counting days, can spiral into centuries of confusion, politics, and outright comedy. Next time, we'll see how one tiny missing minus sign nearly wrecked the work of geniuses. Because if calendars taught us anything, it's that small mistakes can grow into gigantic disasters. And in math, sometimes a single symbol can change everything. Mathematics has a strange sense of humor. It doesn't usually slap you in the face with big errors. No, it prefers to hide mistakes in the smallest details. A tiny slip of the pen, a misplaced decimal, or the most notorious villain of them all, a missing minus sign. And believe it or not, even Isaac Newton himself, the man who invented calculus, the man who figured out gravity, the man whose hair probably contained more genius than most universities, was not safe from this sneaky little symbol. Let's set the stage. Newton lived in the 17th century, a time when Europe was buzzing with new science, telescopes, experiments, discoveries everywhere, and in the middle of it all, Newton, working alone in his farmhouse during a plague outbreak, casually invented calculus. As one does, he also cracked the mystery of planetary motion, explained gravity, and rewrote the laws of physics. Pretty good résumé. But even geniuses make mistakes. Newton, like everyone else, had to wrestle with messy calculations, and sometimes he forgot a minus sign. Seems harmless, right? But in math, leaving out that tiny dash can completely flip your results upside down. Imagine calculating the force of gravity and getting repulsion instead of attraction. Congratulations, you've just invented anti-gravity by accident. One of Newton's most famous slips happened in his work on planetary orbits. When he was crunching the numbers for how planets move around the sun, he made a sign error. For a while, this convinced him that elliptical orbits didn't work the way they actually do. His math suggested something different, something wrong. Thankfully, he caught it later. But for a brief shining moment, even Newton had to stare at his papers and think, wait, did I just break the solar system? And Newton wasn't alone. This missing minus sign problem haunted mathematicians and scientists everywhere. You'd think after writing equations for centuries, humanity would learn to keep track of a tiny symbol. Nope. Sign errors are still one of the most common mistakes in math classes today. Teachers will tell you half of all wrong answers on a calculus test come down to one thing. Someone dropped a minus sign. Newton was basically just a really fancy version of that student. Of course, when the average student makes the mistake, they lose a point. When Newton made the mistake, it threatened to derail the entire understanding of planetary motion. Stakes were a little higher. There's also a delightful irony here. Newton's laws of motion are all about precision, about the universe obeying exact rules. Yet the man himself struggled with one of the tiniest rules of algebra. It's like watching a master chef burn toast. Brilliant, but also human. And it wasn't just Newton. Later scientists made similar errors with devastating consequences. Engineers have miscalculated bridge designs because of a missing minus. Astronomers have pointed telescopes at the wrong coordinates. Even NASA has lost spacecraft over tiny sign and unit mistakes. The lesson is clear. The universe runs on details, and it doesn't care if you're a genius. Now, let's zoom out a bit. Why are minus signs so dangerous? Because they flip meaning. A plus means add, forward, positive. A minus means subtract, backward, negative. Forget one, and your rocket points down instead of up. Your orbit spirals in instead of out. Your equation sings the wrong tune. It's like confusing send with delete in an email. One small keystroke, massive consequences. For students, this is relatable. Everyone's had that moment of proudly finishing a math problem, only to see the teacher mark it wrong because of a missing minus. Brutal, but it's also comforting. If Newton himself did it, maybe we're all in good company. Greatness doesn't mean perfection. There's another angle to this. Newton was famously prickly, even arrogant. He fought bitter rivalries, especially with Leibniz over who invented calculus. He liked to present himself as the ultimate authority. But these little errors remind us that underneath the powdered wig was just a guy scribbling on paper, vulnerable to the same slip-ups as the rest of us. His genius wasn't that he never made mistakes. It was that he caught them, corrected them, and kept going. And here's where the story becomes strangely inspiring. The history of science is littered with small mistakes that led to big truths. Newton's missing minus sign forced him to recheck his work, which eventually gave him more confidence in his laws. Later, other scientists' errors pushed them to refine theories, double-check experiments, and invent new methods. Every minus sign forgotten is a reminder that details matter, and that progress comes from catching ourselves when we stumble. But let's not be too serious. The comedy of it all is that humanity spent centuries worshipping Newton as a flawless genius, when in reality he made the same dumb algebra mistake that still haunts high schoolers. Imagine if modern textbooks admitted that gravity was discovered by a guy who once forgot a minus sign. Suddenly math feels a lot less intimidating. So, what's the takeaway? Newton's missing minus sign wasn't just a slip of the pen. It was proof that even the greatest minds are fallible, that precision is fragile, and that mistakes are part of the game. If Isaac Newton could lose track of a tiny symbol and still change the world, maybe we can forgive ourselves the next time we misplace one. Next time we'll look at a much bigger math fight. Not just a missing symbol, but a full-blown intellectual war. Newton versus Leibniz, the dirty battle over who really invented calculus. Spoiler, it got petty, nationalistic, and kind of hilarious. Every great invention in history comes with a little drama. The telephone had Bell and Gray racing to the patent office. The light bulb had Edison and Tesla bickering like children over toys. But in mathematics, one feud stands above the rest. A feud so bitter, so drawn out, and so incredibly petty that it shaped the entire future of science. I'm talking about the war over who invented calculus. Newton versus Leibniz, England versus continental Europe. A mathematical cage match. So, what is calculus and why was it worth fighting over? In the simplest terms, calculus is the math of change. It's what you use to calculate how fast something is moving at a given instant, or how areas add up under curves, or how planets trace their orbits. Without calculus, modern science wouldn't exist. No physics, no engineering, no rocket ships, no Wi-Fi. It's that important. So of course, two geniuses came up with it around the same time, and then spent years trying to prove the other was a thief. Let's start with Isaac Newton. In the mid-1660s, while hiding from the plague, Newton basically had the most productive quarantine in human history. He invented calculus, worked out gravity, studied optics, and probably also baked sourdough. But here's the catch. He didn't publish his calculus work right away. He kept it in his notebooks, like a secret recipe. Newton was brilliant, but he was also paranoid. He didn't like sharing his ideas until he was absolutely certain, and he definitely didn't like giving rivals ammunition. Enter Gottfried Wilhelm Leibniz, a German polymath, philosopher, diplomat, mathematician, basically a one-man think tank. In the 1670s, Leibniz started working on similar problems, and in 1684 he published his version of calculus. He even gave us the notation we still use today, the fancy Routh integral sign and the D for derivatives. His system was clear, elegant, and user-friendly. Newton's version, by contrast, was messy, clunky, and buried in dense Latin. So when the world first saw calculus, it looked like Leibniz had invented it. That did not sit well with Newton. By the 1690s, rumours were flying. Did Leibniz steal ideas from Newton's unpublished notes? Did Newton crib from Leibniz? The Royal Society in London got involved, and things turned ugly. In 1711, a committee was formed to investigate who invented calculus first. Guess who secretly wrote most of the committee's report? That's right, Isaac Newton himself. The committee shockingly declared Newton the rightful inventor and accused Leibniz of plagiarism, impartial, right. This feud divided Europe. In England, mathematicians rallied behind Newton, insisting he was the true father of calculus. On the continent, scholars sided with Leibniz, praising his elegant notation. The split was so deep that English mathematics fell behind for almost a century. While the rest of Europe advanced science using Leibniz's methods, English mathematicians stubbornly clung to Newton's awkward system out of national pride. It's like everyone else was driving sleek sports cars while England insisted on pedaling a rusty bicycle because we invented bicycles first. The tragedy is that both men were right. In their own way, Newton had developed the fundamental ideas earlier, but Leibniz had published first and created the better notation. In a sane world, they could have shared credit and moved on. But no, pride, ego, and politics turned it into an all-out intellectual war. And the pettiness was legendary. Newton wrote anonymous reviews trashing Leibniz. Leibniz accused Newton of trying to monopolize science. Their supporters wrote pamphlets mocking each other. At one point, someone actually argued that Leibniz's calculus was suspicious because he used too many squiggly symbols. This is what math looked like in the 18th century. Men in wigs angrily debating squiggles. To make matters worse, Leibniz died in 1716, poor and largely disgraced in his own country. Newton, meanwhile, lived on, wealthy and honoured, running the Royal Mint and cracking down on counterfeiters. History, at least at the time, seemed to crown Newton as the winner, but over the years people came to appreciate Leibniz's contributions too. Today his notation dominates. Every time you see whir or dx, you're seeing Leibniz's legacy, not Newton's. In a sense, Leibniz won the war in the long run, even if he didn't get the credit during his lifetime. The calculus feud is one of the great cautionary tales of science. Two brilliant men stumbled on the same groundbreaking idea, but instead of collaborating, they let ego turn it into a brawl. And their students, their countries, even entire scientific traditions got dragged into it. Imagine if Newton and Leibniz had worked together. Science might have advanced decades faster. But no, we got a mathematical soap opera instead. And honestly, there's something darkly funny about it. We like to imagine geniuses as calm, rational, above petty squabbles. But here we see Newton secretly writing hit pieces about his rival, while Leibniz sulks and throws shade in letters. It's proof that even the brightest minds are still human, with all the jealousy and pride that come with the territory. So, who really invented calculus? The answer is both, independently. Newton had the ideas first. Leibniz published and popularized them. The mistake wasn't in their math, but in how they handled the politics. Their feud created a century of division in European science. It's one of history's great what-ifs. What if they had swallowed their pride and shared the glory? But in a way, the feud itself changed the world anyway. It forced mathematicians to pick sides, develop different traditions, and eventually reconcile them. The drama pushed people to sharpen the tools of calculus and spread them further. Even their mistakes, even their bitterness became part of the story of progress. So next time you're sweating over a calculus exam, just remember the people who invented it were too busy fighting each other to enjoy it either. Up next, we're going to leave personal drama behind and jump into a more abstract kind of chaos. The time when infinity itself broke mathematics. Spoiler, it drove some mathematicians completely mad. Infinity. Just saying the word feels dangerous. It's one of those concepts that sounds magical, almost mystical, endless, unbounded, forever. The idea has haunted human thought since the beginning. And in mathematics, infinity has caused more headaches, more arguments, and more mental breakdowns than almost anything else. You'd think a number that means bigger than everything would be easy to handle. Spoiler, it's not. Let's start with the ancient Greeks. They loved geometry, logic, neatness. Infinity did not fit in that world. Zeno of Elea came up with his famous paradoxes. You've probably heard one, Achilles and the tortoise. Achilles runs a race against a tortoise, but the tortoise gets a head start. Every time Achilles reaches where the tortoise was, the tortoise has moved a little further ahead. According to Zeno, Achilles can never catch up. That's infinity messing with your brain. Obviously Achilles does win, but Zeno's paradox showed how dividing time and space into infinite pieces creates nonsense. The Greeks hated that. They wanted math to be clean, and infinity just made a mess. So for centuries, mathematicians avoided infinity. They treated it like Voldemort, the concept that must not be named. They'd say things like, the line goes on without bound, but they wouldn't touch actual infinity with a 10-foot pole. It was too weird, too slippery. Better to leave it alone. Fast forward to the 17th century. Along comes calculus. Suddenly, mathematicians needed infinity. They wanted to calculate areas under curves, slopes at single points, sums of infinite series. Infinity was lurking in every equation. Newton and Leibniz both danced around it, inventing tricks to work with infinitesimals, quantities smaller than any real number, but not quite zero. It was genius, but also shaky. Critics accused them of witchcraft. Bishop Berkeley famously mocked calculus as the ghosts of departed quantities. Translation: you guys are making stuff up. And he wasn't entirely wrong. Calculus worked, but nobody could explain why in a way that made sense. Infinity was breaking math again. But the real explosion came in the 19th century with a man named George Cantor. Cantor did something bold. He didn't just talk about infinity as one vague concept. He studied it, dissected it, and discovered there are different sizes of infinity. This was like announcing there are different types of forever, and people lost their minds. Here's the gist. Imagine counting numbers 1, 2, 3, 4, on and on. That's infinite. Now imagine even numbers 2, 4, 6, 8. That's also infinite. Surprisingly, those two infinities are the same size because you can pair each counting number with an even number. But then Cantor looked at real numbers. Fractions, decimals, everything in between. He proved that this infinity is bigger. You cannot list all real numbers, no matter how hard you try. That means there are infinities so big that the infinity of counting numbers looks small in comparison. Mind blown. Mathematicians were horrified. Some flat out refused to believe him. Famous ones like Leopold Kronecker dismissed Cantor as a crank. Others called his work dangerous, heretical. Cantor himself suffered deeply from the backlash. He spent years in and out of mental institutions, struggling with depression, haunted by the very infinities he had unleashed. Infinity didn't just break math, It broke Cantor's health too. But here's the twist. Cantor was right. His discoveries laid the foundation for modern set theory, which underpins huge parts of mathematics today. Without him, computer science, logic, and much of modern analysis wouldn't exist. The infinities that seemed like madness turned out to be essential. And yet, infinity is still tricky. Even today, mathematicians debate things like the continuum hypothesis, whether there's an infinity between the infinity of counting numbers and the infinity of real numbers. Nobody knows. In fact, it's been proven that within our current system of math, you can neither prove it true nor false. Infinity laughs at our rules. There's also the way infinity shows up in physics. Black holes, the Big Bang, singularity points where equations blow up to infinity. Physicists hate this. Infinity in an equation usually means we don't actually understand what's going on here. It's a giant cosmic error message. And of course, infinity has its lighter side. Kids grasp it instinctively. Ask a child their favorite number and they'll shout, infinity. Ask another and they'll say, infinity plus 1. Congratulations, your living room has just recreated centuries of mathematical debate. So what's the takeaway? Infinity broke mathematics not because it's wrong, but because it's too big for us to handle neatly. It forces us to stretch our minds beyond comfort. The mistakes people made with infinity, avoiding it, misunderstanding it, rejecting it, shaped the development of math itself. Infinity pushed us out of our safe zone. And maybe that's why infinity is beautiful. It humbles us. It reminds us that no matter how clever we are, there will always be things bigger than we can fully grasp. It sips the universe's way of saying, nice try humans, but you sit not done yet. Next time we'll zoom in on another mathematical headache. The parallel postulate, a single stubborn rule in geometry that refused to behave, drove mathematicians crazy, and eventually gave us entirely new ways of seeing space. Mathematicians are a stubborn bunch. Give them a rule that seems obvious, and they'll spend centuries trying to prove it, just to make sure. Sometimes this works out. Other times it creates one of the biggest wild goose chases in math history. And nowhere is that clearer than with the infamous parallel postulate, a single line in Euclid's geometry book that drove people mad for 2,000 years. Let's rewind to ancient Greece again. Euclid, living around 300 BCE, wrote the Elements. This book became the math Bible for centuries. It laid out geometry as a neat system of rules and proofs. Most of it was beautiful, short, elegant, logical, except for one awkward duck, the fifth postulate, also known as the parallel postulate. The postulate basically says this: if you've got a line and a point not on that line, there's exactly one line through that point that never touches the first line. In other words, only one parallel line. Seems obvious, right? You look at your window frame, your notebook, your bookshelf, parallel lines are everywhere. End of story. Except mathematicians didn't like it. The other postulates were short and sweet. Things like a straight line can be drawn between any 2 points. But the parallel postulate was long, clunky, and suspiciously complicated. It felt out of place, like the geometry version of a footnote that grew too long. So for centuries people thought, surely this messy rule must be provable from the others. Surely Euclid included it by mistake. Surely we can get rid of it. Cue 2,000 years of failure. Mathematicians from ancient Greece, India, the Islamic Golden Age, Renaissance Europe, generation after generation, tried to prove the parallel postulate. They twisted diagrams, wrote endless arguments, and always came up short. Some thought they'd succeeded, only for others to point out hidden assumptions. It became the ultimate math obsession, like a never-ending Sudoku puzzle. Why did they care so much? Because geometry was supposed to be perfect, a flawless logical system. If one of its rules seemed wobbly, the whole temple might collapse. And because humans hate loose ends, we'd rather waste centuries chasing a pointless proof than admit something might just stand on its own. But here's the punchline. The problem wasn't that the parallel postulate was too weak. The problem was that it wasn't universal at all. In the 19th century, three men, Gauss, Belair, and Lobachevsky, finally stopped trying to prove it. Instead, they asked, what if it's just wrong? What if space works differently? What if, through a given point, there are many parallel lines, or none at all? Boom. Non-Euclidean geometry was born. Suddenly the old truth of exactly one parallel line turned out to be just one option among many. On a sphere like Earth, there are no parallel lines, eventually everything meets. On a saddle-shaped surface, there can be infinitely many. Geometry wasn't broken, it was bigger than anyone realized. At first, people thought this was nonsense. It felt like heresy against Euclid. But slowly the new geometries proved themselves useful. In fact, when Einstein came along with general relativity in the early 20th century, he used non-Euclidean geometry to describe the curvature of space-time. Without the failure to prove the parallel postulate, we wouldn't understand gravity the way we do today. So for 2,000 years, mathematicians were stuck in a mistake. They believed the postulate had to be provable, when really the world was waiting for them to let go. It's almost tragic. Imagine how many brilliant minds spent their lives chasing this phantom proof, only for the real breakthrough to come from asking a different question entirely. And there's comedy in it too. Think of the pride, the arguments, the wasted ink, all those diagrams of triangles and lines, all for nothing, or rather for something far better. The discovery that the universe isn't locked into Euclid's neat little rules. The mistake was refusing to imagine alternatives. Today we take it for granted. Kids learn Euclidean geometry in school, and mathematicians work with non-Euclidean spaces all the time. But behind that comfort is centuries of obsession, frustration, and stubbornness. The parallel postulate problem is a reminder that sometimes the thing that drives you nuts isn't supposed to be solved. It's supposed to break open your perspective. So next time you get stuck on a problem that won't budge, maybe take a page from Gauss and Friends. Stop trying to force it. Ask instead, what if the rules are different? What if the mistake is assuming it should be provable in the first place? That's when real breakthroughs happen. In the next chapter, we'll trade abstract geometry for something more down-to-earth maps. Because when people tried to flatten the round Earth onto paper, they made mistakes so big, they literally reshaped our view of the world. Maps are magical. They make the world look simple, like you can fold an entire planet into your backpack, a flat sheet of paper, a few lines and colors, and suddenly you've got oceans, mountains, countries, and borders all laid out neatly. But here's the catch. The Earth isn't flat. Sorry, conspiracy theorists. It's a sphere, or close enough. And as soon as you try to flatten a sphere, the math goes wrong. In fact, the history of mapmaking is basically one long story of mathematical fails. Let's start with the basic problem. Imagine peeling an orange. Try to flatten that peel on a table. It rips, stretches, cracks. You can't do it perfectly. Same with Earth. Any flat map has to distort something. Size, shape, distance, direction. Pick your poison. Mathematicians call this the projection problem, and for centuries cartographers struggled with it. Take the famous Mercator projection. Gerardus Mercator, a Flemish cartographer in the 16th century, came up with it for sailors. On his map, straight lines of constant compass bearing appear as straight lines on the page. Super handy if you're navigating across the ocean. The problem, it massively distorts size near the poles. Greenland looks like the size of Africa, when in reality Africa is 14 times bigger. Europe looks larger than South America, when in fact South America crushes Europe in size. Basically, Mercator accidentally invented Eurocentric geography. Convenient if you're European, misleading if you're anyone else. Other projections made different mistakes. The Peters projection tried to fix size distortion, showing countries more accurately by area, noble effort, but it stretched continents into weird shapes. Suddenly Africa looks long and skinny, like someone tugged it with a rubber band. Shapes are sacrificed to save size. The result is technically fairer but ugly and confusing. And then there were the medieval maps, which were less about accuracy and more about, well, vibes. Many had Jerusalem at the center because of religion, and Asia stretched out like a giant pancake. Oceans were drawn more like decorative borders. Some maps even had sea monsters lurking around the edges. To be fair, if you're already drawing dragons, a little distortion in scale probably isn't your top concern. Even great explorers fell victim to math errors. Christopher Columbus famously underestimated the size of the Earth. He thought Asia was much closer than it was, which is why he bumped into the Americas instead. A gigantic mistake, with gigantic consequences. His miscalculation was partly based on using the wrong kind of miles in his math. Yes, there were multiple mile definitions floating around, and Columbus picked the wrong one. That little slip helped reshape global history. And let's not forget longitude. For centuries, nobody knew how to measure east-west position accurately at sea. Latitude was easy. You just measure the angle of the sun or stars, but longitude required precise timekeeping, and clocks didn't work well on rocking ships. The result? Sailors guessed. Badly. Whole fleets got lost or wrecked because they miscalculated their position. The famous 1707 Sigley naval disaster killed nearly 2,000 British sailors when their navigators thought they were somewhere else entirely. It was such a huge failure that the British government offered a massive prize for anyone who could solve the longitude problem. It wasn't solved until John Harrison invented a reliable sea clock in the 18th century. Sometimes, it takes a watchmaker to fix what math can't. What's fascinating is that all these mistakes weren't just errors, they shaped how people saw the world. Europeans grew up thinking Africa was small and unimportant because maps told them so. Colonization and politics were influenced by distorted projections. Our mental image of Earth has been sculpted by math fails as much as by accuracy. Even today, ask someone to picture the globe, and chances are they're imagining Mercator's stretched out version, not the real proportions. And yet, the mess of map math is also kind of beautiful. Every projection is a compromise, a choice of what you value most. Do you want sailors to navigate easily? Use Mercator. Do you want to compare land areas fairly? Use Peters. Want to keep shapes looking natural? Use Robinson. None are perfect because perfection is impossible. Flattening Earth will always break something. Here's a fun modern twist. In 2016, an animation went viral showing how countries shrink and expand when switching from Mercator to Peters. People were shocked. What do you mean Africa is that big? What do you mean Greenland is tiny? The truth had been hidden in plain sight for centuries, disguised by a projection error. A math fail that became part of our collective worldview. So what's the lesson here? Sometimes mistakes aren't just accidents, they're baked into the system. With maps, distortion is inevitable. The only mistake is pretending your projection is the truth. Mercator never meant his map to be used in classrooms for geography. It was for navigation. But once people started treating it as the default, it became a silent bias that shaped generations. In the end, mapmakers' math fails remind us of a bigger truth. We don't just measure the world, we imagine it. And those imaginations, even when wrong, have power. They guide explorers, influence politics, and change how we see ourselves in relation to others. The errors are as much a part of history as the corrections. Next time we'll leave the high seas behind and enter the battlefield, because sometimes math mistakes don't just distort maps, they start wars. War is usually blamed on politics, greed, or human stubbornness, but sometimes the spark isn't a speech or a treaty. Sometimes it's a math problem. That's right, humanity has actually managed to stumble into war because somebody got their numbers wrong. It sounds absurd, but history is full of cases where miscalculation quite literally cost lives. One of the most famous examples comes from World War II. In 1941, Hitler launched Operation Barbarossa, the invasion of the Soviet Union. German planners calculated it would take just a few months. They expected to conquer Moscow before winter. Their math for supplies, troop strength and distances was based on optimism and hubris. They assumed the campaign would be short and sweet. Spoiler, it wasn't. Their numbers were way off. Russia's size, its brutal winters, and the sheer resilience of the Red Army destroyed those calculations. Millions of lives were lost because leaders trusted bad math. But let's go further back. In 1707, the British Royal Navy suffered one of its worst disasters near the Isles of Scilly. Admiral Sir Cloudesley Shovel, yes, that was really his name, was leading a fleet home from battle. His navigators miscalculated their longitude. Without accurate clocks at sea, they simply guessed their position. Their guess was wrong. The fleet smashed into rocks. 4 warships sank. Nearly 2,000 sailors died. It didn't start a war, but it showed how dangerous mathematical mistakes at sea could be. In fact, this disaster spurred the famous Longitude Act, offering a massive prize for anyone who could solve the longitude problem. Another case of math gone wrong happened in World War I. In 1914, Austria-Hungary declared war on Serbia after the assassination of Archduke Franz Ferdinand. Sounds straightforward, except Austria-Hungary's generals made a huge logistical miscalculation. They assumed moving troops across their empire would be easy, but their rail schedules were a nightmare. Trains weren't coordinated, supplies went missing, soldiers ended up in the wrong places. The entire opening campaign was crippled by bad arithmetic. Historians often say WWI spiraled out of control because of alliances and politics. True, but also because some generals couldn't count train timetables properly. And then there's the story of the Battle of Karen Sebez in 1788, during the Austro-Turkish War. This wasn't exactly caused by miscalculated numbers, it was caused by miscalculated communication, which is just another form of math fail. Austrian troops got drunk, mistook each other for the enemy, and opened fire on themselves. Thousands died in chaos. A war lost because someone miscounted who was friend and who was foe. Tragic, but also absurd. Here's another gem. The Maginot Line. In the 1930s, France poured resources into building a massive line of fortifications along its border with Germany. The math was simple. Germany invaded through that border in World War I, so reinforce it, and they'll never get through again. Billions of francs, endless engineering, miles of bunkers. The problem: the planners forgot to extend the line through the Ardennes forest. They assumed it was impenetrable. German generals did the math differently. Tanks rolled right through in 1940. France fell in 6 weeks. That's what you call a billion-dollar arithmetic mistake. What's fascinating is how often these mistakes come down to overconfidence. Leaders believe their numbers, but their numbers are based on bad assumptions. Napoleon's march into Russia in 1812 is another classic. He calculated supplies for a quick campaign, not a drawn-out slog through winter. His math said the army would survive. Reality said otherwise. Out of 600,000 troops, fewer than 100,000 made it back. Infinity may break mathematicians' brains, but Russian winters break armies. And it's not just Europe. In the American Civil War, both Union and Confederate generals repeatedly miscalculated enemy strength. They often doubled or halved estimates. Battles were lost not because of courage or weapons, but because someone's math was off by a few thousand soldiers. The fog of war is really the fog of bad arithmetic. So what do we learn here? War isn't just fought with swords, guns, or tanks. It's fought with numbers, supplies, distances, timetables, troop counts. And when the numbers go wrong, everything collapses. A missing digit can kill as surely as a bullet. And yet, there's irony in this too. These math mistakes didn't just cause disasters, they reshaped history. If the Germans had calculated Barbarossa correctly, maybe they wouldn't have invaded. If Napoleon had planned better, maybe he'd have held Europe longer. If the Maginot Line had worked, maybe World War II would have looked completely different. The mistakes didn't just destroy plans, they created new futures. It's almost comforting in a strange way. Humanity's biggest wars weren't just about evil or ambition. They were also about human fallibility. Even the greatest generals with all their power couldn't escape the curse of bad math. So the next time you hear about some giant military campaign, remember this. Behind the grand speeches and flags, there's probably a poor officer somewhere with a calculator, sweating bullets, praying he didn't miss a minus sign. Because as history shows, sometimes wars don't start with gunfire, they start with arithmetic. Next time we'll look at a disaster that didn't need a battlefield at all. A bridge so famous, so iconic, that when it fell it became the poster child for engineering mistakes. Yes, we're heading to the story of the bridge that shouldn't have fallen. Bridges are supposed to be symbols of triumph. They connect cities, unite people, and show off human engineering. But every so often, bridges also show off something else. Our mistakes. And one of the most famous examples is the Tacoma Narrows Bridge, also known as Galloping Gertie. Built in 1940, collapsed in 1940. That's right, it survived only 4 months before wobbling itself into the history books. So what went wrong? The math, of course. When engineers designed the Tacoma Narrows Bridge in Washington state, they wanted it sleek and elegant, long, thin, flexible. They did the calculations to make sure it would hold weight. Structurally, on paper, everything looked fine, but they forgot one crucial factor: wind. Not hurricane wind, not storm wind, just a steady breeze. That steady breeze turned the bridge into the world's largest trampoline. The bridge began to twist and bounce dramatically, earning its nickname Galloping Gertie. Drivers described it as like riding a roller coaster every time they crossed. People actually avoided it because it was so terrifying. You'd pay your toll and then pray. Some folks even crossed on foot just for the thrill, like it was an amusement park ride. On November 7th, 1940, the inevitable happened. The wind picked up, the bridge began to oscillate violently, and then it tore itself apart, in a scene captured on film. One of the most famous engineering disaster videos ever. The roadway twisted like a ribbon before breaking into pieces and crashing into the river below. Miraculously, only one life was lost. A dog named Tubby who was trapped in a car. Tubby became the tragic mascot of mathematical miscalculation. So where exactly did the math fail? The engineers underestimated a phenomenon called aeroelastic flutter. In simple terms, when wind passes over a flexible structure, it can create vibrations. If those vibrations match the structure's natural frequency, they amplify, like a singer shattering a glass with the right pitch. The Tacoma Narrows Bridge was basically an opera stage for the wind. The math didn't fully account for this resonance. The result, disaster. But here's the interesting part. The failure wasn't just a tragedy. It was a lesson. The collapse of Galloping Gertie revolutionized engineering. It forced designers to take aerodynamics seriously in large structures. From then on, bridges and skyscrapers had to pass wind tunnel tests. Engineers developed new equations, new models, and new safeguards. In a sense, Tubby's sacrifice wasn't in vain. Every safe bridge built afterward owes something to that mistake. And the Tacoma Narrows isn't the only bridge math fail in history. In 1850, the Angers Bridge in France collapsed when a storm hit. The soldiers marching across it were in perfect step, which amplified the bridge's natural vibrations. Nearly 200 people died. Afterward, armies around the world introduced a new rule: break step when crossing a bridge. Even today, soldiers deliberately shuffle their rhythm so they don't accidentally turn a bridge into a tuning fork. Then there's the Quebec Bridge in Canada. Built in the early 20th century, it collapsed not once, but twice. The first time was in 1907, killing 75 workers. Investigators found that the math underestimated the bridge's weight. They simply hadn't accounted for how heavy it would be. They rebuilt it, only for a second collapse in 1916, killing another 13 workers. Third time's the charm. The bridge finally opened in 1917. It's still standing today, but it carries the ghosts of its earlier failures. What's fascinating is how small errors balloon in massive projects. A tiny miscalculation in stress, a missing safety factor, an overlooked force of nature. On paper, they look like footnotes. In reality, they mean collapse, chaos, and sometimes tragedy. Bridges don't forgive sloppy arithmetic. And yet, there's something strangely inspiring about these disasters. They show the power of learning from mistakes. Every failure became a case study. Engineering students still study Tacoma Narrows, Quebec, Angers, and others. Each one added new chapters to the textbook of structural design. Today's suspension bridges like the Golden Gate or Akashi Kaikyo in Japan stand tall because of lessons learned from bridges that didn't. There's also a touch of human comedy in it. The film of Galloping Gertie collapsing has been shown to generations of students, almost like a slapstick routine. The bridge twists, cars slide, pieces break off. It looks unreal. But the humour masks the seriousness. This was math gone wrong in a very public, very expensive way. The moral is simple. Big projects demand humble math. If you underestimate nature, nature wins. Engineers today don't just calculate loads and stresses. They calculate uncertainty. They overbuild, they test, they simulate, because they know the ghosts of Galloping Gertie are still out there, whispering, "Don't forget the wind." So next time you cross a bridge, maybe give a little nod to the mistakes of the past. Your safe, steady journey is built on the ruins of math errors that shook, cracked, and collapsed before. And next time we'll move from physical structures to digital ones. Because when computers started doing math for us, we assumed they'd be flawless. Spoiler, they weren't. And some of their early mistakes were catastrophic. There was a time when people thought computers would save us from mistakes. No more human error, no more missed minus signs, no more tired scribes smudging ink on their ledgers. A machine that could calculate tirelessly, flawlessly, forever. That was the dream. And then reality came along, and the computers said, no. Here's the thing about computers. They don't actually understand math. They just follow instructions. Perfectly. Which means if your instructions are wrong, the computer will happily march off a cliff, dragging you with it. Garbage in, garbage out. Some of the biggest math mistakes in modern history weren't made by humans with chalkboards. They were made by machines faithfully executing bad math. Take the Patriot missile disaster in 1991. During the Gulf War, the US military deployed Patriot missile defense systems to protect troops from incoming Scud missiles. The system worked by calculating the position of enemy missiles using a clock. Sounds fine, right? Except the clock's math was slightly off. It measured time in tiny units, and the conversion from binary to decimal introduced a rounding error. A rounding error so small it seemed harmless. But after running continuously for 100 hours, that tiny error added up to a time shift of about 1/3 of a second. Doesn't sound like much until you realize a Scud missile travels more than 1,500 meters in that time. On February 25th, a Scud hit an American barracks in Dhahran, Saudi Arabia. The Patriot had missed. 28 soldiers died, all because of a rounding mistake. Or consider the Ariane 5 rocket explosion in 1996. The European Space Agency had spent a decade and nearly $8 billion developing this beautiful, massive rocket. Its first flight was supposed to be a triumph. Instead, 37 seconds after liftoff, the rocket veered off course, broke apart and self-destructed. Why? A computer program tried to stuff a 64-bit number into a 16-bit space. Think of it like trying to shove a watermelon into a mailbox. The computer crashed, sent nonsense to the guidance system, and the rocket went boom. $500 million gone in under a minute. The cause? A data conversion error. Then there's the Mars Climate Orbiter in 1999, a classic case of unit confusion. One team at Lockheed Martin used imperial units, pounds of force, while NASA expected metric newtons. The software dutifully crunched the numbers, but they didn't match reality. When the spacecraft arrived at Mars, it dipped too low into the atmosphere, burned up, and was lost forever. Price tag: $125 million. Cause: failure to convert feet to meters. That's not just a mistake. That's the kind of math fail your high school teacher warned you about. Computers have also been blamed for financial meltdowns. In 2012, Knight Capital Group, a big trading firm on Wall Street, unleashed a software update with a bug. The program went haywire, buying and selling millions of shares at random. In 45 minutes, Knight Capital lost $440 million. The company collapsed, all because of a few bad lines of code. It wasn't even malicious, just sloppy math logic. And here's the funnier side. Not all computer math errors are deadly serious. Sometimes they're just weird. Ever see your calculator spit out 1.00000000000 when you expected exactly 1? That's floating point error. Computers can't represent some decimals precisely, so they fudge it. It doesn't matter much when you're adding lunch receipts, but in scientific simulations, those tiny errors can snowball into chaos. One physicist joked that floating point math is basically lying, but politely. The irony is delicious. We built computers to escape human error, but all we did was move the mistakes into silicon. Now they're faster, more precise, and often harder to catch. A typo in code can ruin a rocket launch, crash a stock market, or lose a spacecraft. And unlike humans, computers don't raise a hand and say, excuse me, this doesn't look right. They just execute perfectly wrong. But let's not be too harsh. Every failure taught us something. The Patriot disaster pushed engineers to design better timekeeping systems. Ariane 5 forced software teams to test conversions more carefully. The Mars orbiter mishap hammered home the importance of unit consistency, something NASA triple checks now. Each computer said no moment improved the technology, even if it came at a painful price. And let's admit it, these mistakes make computers more human. We like to imagine machines as cold and flawless, but in practice, they're just as quirky as we are. They trip over decimals, get confused by conversions, and choke on bad instructions. Computers are like that brilliant student who always shows their work perfectly, but if they misread the question, they ace the wrong problem. So the next time your laptop freezes or your phone autocorrects something ridiculous, remember this is part of a grand tradition. Computers saying no is as old as computers themselves. It's annoying, sure, but it's also comforting. Even our smartest machines can't escape the beauty of mistakes. Next time we'll look at statistics, because nothing breaks trust quite like numbers that lie. And as we'll see, bad stats have fooled everyone from scientists to governments to everyday people trying to make sense of the world. There's a famous saying, there are 3 kinds of lies: damned lies, and statistics. And honestly, statistics has earned that reputation. Numbers look so trustworthy on paper. They wear little lab coats and glasses. They feel objective, scientific, undeniable. But the truth is, statistics can be twisted, bent, and downright abused. And when that happens, the lies they tell can change history. Let's start with something simple. Imagine you walk into an ice cream shop. They tell you that 90% of customers say their ice cream is the best in town. Sounds convincing, right? Until you learn they only asked 10 people and 9 of them were employees, That's statistics lying to you, or rather, people using statistics to lie. One of the most infamous cases of misleading statistics comes from smoking. For decades, tobacco companies funded studies that claimed smoking wasn't really harmful. They cherry-picked data, massaged numbers, and presented graphs that looked reassuring. Meanwhile, lung cancer rates skyrocketed. It wasn't that the math was wrong. It was that the math was bent to serve an agenda. Statistics became a weapon of persuasion, not truth. Another classic example is crime statistics. A government might proudly announce crime has dropped 20% in the last year. Sounds great. But maybe they only changed how crimes were recorded, or maybe minor offences dropped while violent crime actually rose. The numbers are technically true, but the story they tell is false. It's like bragging that you lost weight, when really you just changed your scale to read lighter. During World War II, a brilliant statistician named Abraham Wald faced a problem. Allied bombers were getting shot down, and the military wanted to reinforce the areas most often hit by bullets. They showed Wald data from planes that returned from missions, with bullet holes concentrated in the wings and fuselage. So, we should reinforce those spots, right? Wrong, said Wald. The planes with bullet holes in those spots were the ones that survived. The ones that got hit in other places never made it back. Wald realized the military had fallen for survivorship bias. Reinforce the areas with no bullet holes, that's where the real danger was. His statistical insight saved lives, but it also showed how easily even smart people can be fooled by incomplete data. Then there's the world of medical research. Clinical trials often report relative risk instead of absolute risk. For example, a drug might reduce your chance of a certain disease by 50%. Wow, half. But if your original risk was only 2 in 1,000, now it's 1 in 1,000. The improvement is real, but the statistic makes it look way more dramatic. Advertisers love this trick. Patients, not so much. Statistics can also backfire spectacularly. In the 1950s, a researcher named Anshel Keys published studies linking fat intake to heart disease. His work shaped decades of dietary advice, low-fat everything, but it turned out his data was cherry-picked. He left out countries where fat consumption was high, but heart disease was low. For years, people avoided butter and cheese, only to later learn that sugar might have been the bigger villain all along. Statistics lied, and entire diets were built on that lie. Sometimes the lies are unintentional. The famous correlation is not causation problem. Ice cream sales and drowning deaths both rise in the summer. Does that mean ice cream causes drowning? Of course not. The real cause is hot weather. But if you just look at the numbers, the correlation seems strong. Whole books of silly correlations have been published, like margarine consumption correlating with divorce rates in Maine. Statistically true, completely meaningless. And let's not forget polling. Politicians live and die by poll numbers, and yet polls are notoriously slippery. Ask a question one way, you get one answer. Rephrase it slightly, you get the opposite. In 1948, every major poll predicted Thomas Dewey would beat Harry Truman for president. Newspapers even printed the famous headline, "Dewey defeats Truman." Except Truman won. The polls had stopped sampling too early and missed a late surge. The photo of Truman grinning and holding up that wrong headline is now an icon of statistical embarrassment. The problem isn't that statistics are evil. The problem is that humans interpret them badly. We see patterns where none exist. We want numbers to confirm our beliefs. We trust graphs more than our own eyes. And sometimes people deliberately exploit that trust. Yet, here's the twist. For all its lies, statistics also gives us truth, when used carefully. Epidemiology, weather forecasting, economics, sports analytics, these fields all rely on statistics done right. The mistakes, the lies, the bad charts, they forced statisticians to refine their methods, to guard against bias, to invent new tools. The very failures of statistics have made it stronger. And maybe that's the comforting part. Numbers aren't magic, they're just tools. They can be sharp and precise or blunt and misleading. The trick is learning how to spot the lies. Once you know the tricks, tiny sample sizes, cherry-picked data, sneaky percentages, you start to see through the smoke. So the next time someone throws statistics at you, don't just nod, ask questions. Who collected the data? How big was the sample? What's being compared? And most importantly, what story are they trying to tell? Because as history shows, numbers can lie as easily as words. Next time we'll leave statistics behind and head into space, because in 1999, NASA learned the hard way that even rocket scientists can make mistakes, especially when one team uses metric units and the other uses imperial. Space exploration is supposed to be the pinnacle of human precision. Rockets, satellites, orbit calculations, everything has to be perfect, down to the tiniest decimal. One wrong number, and your spacecraft doesn't just miss its target, it disappears into the void, which is exactly what happened to NASA in 1999, when they lost the Mars Climate Orbiter, cause of death, a $125 million unit error. Let's set the scene. The Mars Climate Orbiter was supposed to be a state-of-the-art probe, studying the Martian atmosphere and acting as a communications relay for other missions. It launched beautifully, traveled 416 million miles without a hitch, and then, as it approached Mars, everything went sideways. Literally, the spacecraft dipped too low into the Martian atmosphere, burned up, and was gone forever. One of NASA's most embarrassing faceplants. So, what happened? The problem was so small, it's almost laughable. One engineering team, Lockheed Martin, was doing calculations in imperial units, pounds of force. NASA's navigation team, meanwhile, was expecting metric units, newtons, pounds versus newtons, feet versus meters, America versus the rest of the planet. Somewhere in the software, nobody bothered to convert. To put it simply, the spacecraft's brain thought it was being nudged one way, but in reality it was being nudged much harder. By the time it reached Mars, it was on the wrong trajectory. Instead of gracefully sliding into orbit, it took a fiery nosedive. Years of work, $125 million, countless late nights, and poof, gone in seconds. The kicker is that NASA actually suspected something was off. Engineers noticed odd navigation data weeks before arrival, but they trusted the numbers, assuming the spacecraft was fine. After all, the math said it was, except the math was bilingual, and nobody translated. This wasn't just a technical glitch, it was a culture problem. Different teams, different systems, different assumptions. Everyone assumed someone else had double-checked. It's the classic human mistake. Overconfidence in the numbers. If Newton's downfall was a missing minus sign, NASA's was a missing convert to metric. And the embarrassment was global. Headlines mocked NASA for losing a spacecraft because of a math error you'd expect in a high school physics class. Late-night comedians had a field day. Even NASA admitted it was a painful lesson. The units thing has become law, one engineer said later. Everyone was amazed we didn't catch it. But here's the weird beauty of it. That mistake changed how NASA operates. After the Mars Climate Orbiter fiasco, NASA instituted stricter checks, standardized units, and improved cross-team communication. Future missions to Mars, the rovers, the landers, the orbiters, were all run with those lessons in mind. In a sense, the Lost Probe became a $125 million training course. Expensive, yes, but effective. And it's not like NASA is alone. Unit errors have tripped up engineers for centuries. In 1983, an Air Canada flight ran out of fuel mid-air because the ground crew calculated fuel load in pounds instead of kilograms. The plane turned into a giant glider, landing safely only by sheer skill and luck. Known today as the Gimli glider, it's one of the most famous near disasters in aviation. Again, the culprit: units. Or think of medicine. Hospitals have had cases where dosages were prescribed in milligrams instead of micrograms, a thousand-fold difference. Lives have been lost because someone forgot to check units. Math may be universal, but measurement systems are not, and when they collide, chaos follows. There's also something symbolic about NASA's mistake. Here we were, reaching for Mars, one of humanity's greatest dreams, and we tripped over a ruler. The vastness of space didn't kill the probe. Human sloppiness did. It's humbling, almost poetic. And yet, in a way, it makes space exploration more relatable. We imagine rocket scientists as flawless geniuses, but here's proof they make the same kinds of mistakes the rest of us do. Forgetting to convert units is basically the interplanetary version of forgetting to carry the one. Expensive, yes, but deeply human. So what's the lesson? Always check your units. Always. If one team says pounds and the other says newtons, don't just nod, make sure the math speaks the same language. Because as NASA learned the hard way, the universe doesn't care about our unit systems. Mars won't cut you slack because you measured in feet instead of meters. Space is unforgiving, and it will expose every tiny mistake. But here's the silver lining. The Mars Climate Orbiter's fiery end wasn't the end of NASA's Mars dreams. If anything, it set the stage for bigger successes. Spirit, opportunity, curiosity, perseverance. Those rovers owe part of their success to the lessons learned from that burned-up probe. Failure paved the way for triumph. So the next time you hear someone say it's not rocket science, remember that even rocket science sometimes boils down to a simple conversion error. And when it does, the price tag isn't just embarrassing, it's astronomical. Next time we'll leave space and head back down to Earth, into the chaos of financial markets. Because if you think a $125 million mistake is bad, wait until you see what happens when entire economies miscalculate. Money and math have always been best friends. You can't have one without the other. Budgets, interest rates, profits, losses, it's all just numbers. But here's the catch. When the math goes wrong, money doesn't just vanish from your wallet. Whole economies can collapse. And history has shown again and again that the financial world is especially good at turning bad equations into global meltdowns. Let's start with the Black-Scholes model. Back in the 1970s, economists Fisher Black, Myron Scholes and Robert Merton came up with a formula to price options, complex financial contracts that let you bet on future stock prices. Their math was elegant, groundbreaking, and so impressive that Merton and Scholes won the Nobel Prize. Traders loved it. Finally, a way to tame risk with equations. Except reality doesn't always play nice with math. The Black-Scholes model assumed markets behaved rationally, like polite dinner guests. Prices moved smoothly, volatility stayed manageable, and everyone followed the rules. But in real life, markets are more like toddlers at a birthday party. Chaotic, unpredictable, and prone to sudden tantrums. When traders used the formula without caution, they built mountains of risky bets on a foundation that couldn't handle surprises. The most famous collapse tied to this was long-term capital management in 1998. This hedge fund, run by some of the smartest financial minds in the world, including 2 Nobel Prize winners, believed they had mastered risk. Their computers crunched equations all day long, profits soared, and then, boom, Russia defaulted on its debt, markets panicked, and all the impossible events the model said would never happen, happened. LTCM lost billions almost overnight. The US Federal Reserve had to organize a bailout to prevent global financial collapse. The lesson: even brilliant math can be useless if the assumptions are wrong. Fast forward to 2008, the global financial crisis. Banks and investors around the world piled into mortgage-backed securities, believing they were safe. Why did they believe this? Because of math models that rated them as low risk. Equations said homeowners wouldn't all default at once. Equations said housing prices would always go up. Equations said slicing risky mortgages into little pieces magically made them safe. Spoiler, the equations were wrong. When the housing bubble burst, the models crumbled, trillions of dollars evaporated, entire economies tanked, millions lost their homes and jobs. And let's not forget the flash crash of 2010. In May of that year, the US stock market suddenly plunged nearly 1,000 points in minutes, only to recover almost as quickly. The cause: algorithms. Computers programmed to trade stocks at lightning speed got caught in a feedback loop. Sell orders triggered more sell orders, and the market spiraled down. Nobody really understood what was happening in real time. Billions of dollars vanished and reappeared within half an hour. It was like watching the stock market have a nervous breakdown live on TV. The scary thing is, these math meltdowns often start with confidence. Traders, bankers, economists, they trust the formulas. They believe the risk is controlled. They put blind faith in spreadsheets. And the bigger the numbers get, the bigger the mistakes. A student losing $50 on a bad calculation is a bummer. A hedge fund losing $50 billion is a global crisis. There's also comedy in the absurdity. Imagine explaining to an ordinary person in 2008, we crashed the world economy because we believed a formula that said giving giant loans to people who couldn't pay them back was safe. It sounds like satire, yet it happened, and the kicker is that many of the people who created those formulas admitted later they didn't expect anyone to use them so recklessly. They thought their math was a tool, not a holy scripture. But once money gets involved, math mistakes grow legs and run wild. Of course, not all financial math fails are this epic. Sometimes they're just embarrassing. In 2012, JP Morgan lost $6 billion in what became known as the London whale incident. A trader made gigantic bets with flawed risk models. The math said the trades were safe. The reality said otherwise. Boom. Billions gone. So what do we take from this? The stock market is basically a giant math experiment running in real time, with everyone betting their livelihoods on the outcome. And sometimes the equations guiding it are wrong, not because the math itself is broken, but because the assumptions behind it are too simple, too optimistic, or too blind to human behavior. But here's the strange silver lining. Every crash teaches lessons. The 1998 LTCM collapse showed the danger of over-reliance on fancy models. The 2008 crisis forced regulators to rethink risk ratings and banking rules. The flash crash exposed the perils of high-speed trading. Each meltdown was painful, but each one made the system, at least in theory, a little stronger. And maybe that's the big lesson. Money may run on math, but it's still human at its core. Greed, fear, overconfidence, those emotions slip into the equations no matter how precise they look. The math may promise certainty, but reality always has the last laugh. Next time we'll look not at money but at machines that think, artificial intelligence. And the mistakes we're making today might be even bigger than a stock market crash, because when algorithms get it wrong, the consequences could reshape the future itself. For most of history, math mistakes were human. A scribe forgot a zero, a general miscounted troops, an engineer underestimated the wind. But now we live in a new era, the age of artificial intelligence. Machines crunch the numbers for us, learning patterns, spotting connections, and making predictions faster than any human could. Sounds great, right? The problem: when AI makes mistakes, they're not just little slips. They can be massive, invisible, and baked into systems that affect millions of people. Welcome to the wrong equations of tomorrow. Let's start with a simple truth. AI doesn't think. It doesn't understand math the way humans do. It just eats data and spits out patterns. If the data is biased, incomplete, or wrong, the AI learns wrong equations, and it applies them with total confidence. A human might hesitate. AI never does. It's like that overconfident friend who gives terrible directions but insists they're right. Only instead of getting lost on the way to a restaurant, you get entire industries making disastrous decisions. Take facial recognition. The math behind it seemed flawless. Train algorithms on millions of faces, and they'll learn to recognize anyone. But the training data was skewed. Too many light-skinned faces, not enough darker-skinned ones. The result? AI systems that misidentified people of color at alarming rates. Some were even used by police, leading to wrongful arrests. That's not just a bug, that's math encoding bias into justice. Or consider hiring algorithms. Companies eager to save time started letting AI sift through resumes. The idea was to find the best candidates using data from past hires. Sounds efficient, except the data reflected old biases, mostly men, often from certain schools. The AI learned those biases as rules. Women's resumes were downgraded, even if they were equally qualified. The wrong equations of yesterday turned into the wrong equations of tomorrow. And then there's finance. High-frequency trading algorithms now make millions of decisions in fractions of a second. They're guided by math so complex that even their creators don't fully understand it. When something goes wrong, markets can plunge in seconds. Remember the 2010 flash crash? That's child's play compared to what could happen if multiple AIs spiral into feedback loops. Imagine billions of dollars evaporating in less time than it takes you to blink. That's not just math mistakes. That's math moving faster than humans can correct. Healthcare has its own horror stories. AI systems trained to detect diseases sometimes pick up on the wrong signals. One algorithm designed to spot pneumonia risk turned out to rely heavily on whether patients had been admitted to the hospital previously, not on actual medical markers. The result? It flagged healthy people as sick and sick people as fine. Doctors who trusted the machine risked making deadly errors. And let's not forget self-driving cars. These marvels are basically rolling bundles of equations, constantly calculating distances, speeds, and probabilities. Most of the time they work impressively well, but when they fail in ways no human would. One AI car mistook a white truck side for bright sky and plowed right into it. Another failed to recognize a pedestrian pushing a bicycle. These aren't little mistakes, they're life or death miscalculations of reality. What's chilling is that many of these systems are black boxes. With traditional math, you can point to the equation and see where it went wrong. With AI, the math is buried in millions of parameters spread across neural networks. If it spits out nonsense, you might not even know why. It's like having a calculator that sometimes lies to you, but you can't open it up to check the circuitry. And yet, just like every other math mistake in history, these wrong equations aren't just disasters, they're also lessons. The early failures in facial recognition forced researchers to confront bias in datasets. The hiring fiascos pushed companies to rethink what qualified really means. The mistakes of AI are showing us, in real time, how dangerous it is to blindly trust numbers without understanding where they come from. But here's the scary part. Unlike Newton's missing minus sign or NASA's metric mishap, AI mistakes don't just affect one scientist or one probe, they can scale instantly. A bad model used across hospitals could misdiagnose thousands of patients. A biased policing algorithm could ruin countless lives. A glitch in financial trading could crash the global economy. When AI gets it wrong, the ripple effects are enormous. And let's be real, we're still rushing ahead. Companies race to deploy AI faster than regulators can keep up. Everyone wants the benefits: efficiency, profit, convenience. But we haven't figured out how to handle the risks. In a way, it feels like we're living in the middle of a new parallel postulate problem. We're building whole systems on assumptions we haven't fully tested. Only this time, the assumptions aren't about geometry. They're about whether machines can replace human judgment. So what's the lesson here? The wrong equations of tomorrow won't come from forgetting a minus sign. They'll come from trusting machines we don't fully understand. They'll come from assuming data is neutral when it's not. They'll come from racing to implement algorithms before we've checked their consequences. But maybe, just maybe, that's not all bad. Every mistake forces us to slow down, to rethink, to add safeguards. Just like galloping Gertie taught engineers about wind, AI's failures are teaching us about bias, transparency, and responsibility. The wrong equations of tomorrow could still shape a better future if we're willing to learn from them. Next time we'll wrap it all up. Because after all these disasters, miscalculations, and hilarious blunders, we need to ask, why are mistakes so essential to progress? Why being wrong might actually be the best way to be right. We've traveled a long road together, from Babylonian sheep counters to NASA rockets, from Roman numerals to artificial intelligence, and through it all, one pattern keeps showing up. Humanity makes mistakes. Constantly, big ones, small ones, hilarious ones, tragic ones. And yet, if you zoom out, something strange emerges. The mistakes didn't just hold us back, they pushed us forward. Being wrong has been humanity's secret weapon all along. Think about it. The Egyptians gave the year 360 days. Wrong, but in trying to fix it, they invented calendars that let civilizations plan harvests and festivals. The Greeks worshipped geometry as perfect truth, only to discover centuries later that it was built on shaky assumptions. Wrong, but that wrongness led to non-Euclidean geometry and eventually Einstein's theory of relativity. The Romans clung to numerals that were utterly impractical. Wrong, but when Europe finally ditched them, it unlocked modern math and science. Zero was once seen as dangerous. Infinity drove people mad. Pi made mathematicians tear their hair out. All wrong turns, all frustrations, all puzzles that seemed unsolvable. And yet they shaped entire branches of knowledge. Without those struggles, math would be a shadow of itself. Mistakes weren't detours. They were the road. Even the disasters we laughed at had hidden gifts. The Tacoma Narrows Bridge collapse forced engineers to rethink aerodynamics. NASA's Mars Climate Orbiter fiasco taught us the importance of unit consistency. Financial crashes exposed flaws in models and made regulators at least try to improve. Every faceplant became a stepping stone. Humanity advanced, not in spite of mistakes, but because of them. And here's the deeper truth. Being wrong makes us curious. If everything worked perfectly the first time, we'd have no reason to dig deeper. Archimedes wouldn't have invented clever methods to trap pi. Cantor wouldn't have revealed different sizes of infinity. Gauss, Bolyai, and Lobachevsky wouldn't have dared to imagine a universe where parallel lines don't behave. Wrongness pokes us, annoys us, forces us to ask questions, and sometimes those questions crack open entirely new worlds. Of course, mistakes are painful in the moment. Imagine the poor engineer who realized he forgot to convert pounds to newtons, or the generals who lost fleets to bad longitude math, or the mathematicians who wasted decades chasing the parallel postulate. They probably didn't feel like heroes, but history turned their wrongness into progress. They became the cautionary tales, the teachers, the invisible helpers who paved the way for others. There's something comforting about that. It means we don't have to fear mistakes so much. Sure, we should try to avoid them. Nobody wants collapsing bridges or crashing rockets. But we can also recognize that mistakes are part of learning, part of growth, part of what makes discovery possible. In a way, mistakes are proof we're pushing the boundaries. It also makes math feel more human. Too often, math gets painted as cold, rigid, unforgiving. But the history of math is messy, funny, full of blunders. It's humans scribbling diagrams, misplacing minus signs, misinterpreting data, and then stumbling into genius. It's trial and error on a cosmic scale. Math isn't just about getting it right. It's about learning from all the times we got it wrong. So why is being wrong the best way to be right? Because it keeps us humble. It reminds us that we don't know everything, that that the universe is bigger and stranger than our tidy rules. It forces us to adapt, rethink, invent, and it connects us to the long chain of humanity, all the generations before us who also messed up, laughed at themselves, and carried on. Maybe that's why stories about mistakes are so satisfying. They're not just cautionary tales, they're proof of resilience, proof that progress isn't a straight line. It's more like a doodle, loops, scribbles, detours, but somehow it still moves forward. So the next time you make a mistake, whether it's on a math test, at work, or just trying to follow a recipe, remember you're in good company. Newton forgot a minus sign. NASA lost a spacecraft. Entire civilizations miscalculated the length of the year. And yet, the world kept spinning, and knowledge kept growing. Maybe being wrong is what makes us right in the end. And with that, we've reached the end of our journey through the biggest mistakes in math. Thank you for coming along, for laughing at the blunders, and for seeing the hidden beauty in all the wrong turns. Because if there's one thing history proves, it's this: the road to truth is paved with mistakes. And that's not a bug, it's the feature.